Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will discuss another problem. So let me give you the problem first, then we will discuss the solution. So the problem goes like this. A molecule of water vapor H2O has an electric dipole moment of magnitude P equal to 6.2 into 10 raised power minus 30 coulomb meter. Let me change the color. Figure 1 is a representation of this molecule showing the 3 nuclei and the surrounding electron clouds. Then problem says the electric dipole moment P is represented by a vector on the axis of symmetry. The dipole moment arises because the effective center of positive charge does not coincide with the effective center of negative charge. Then part A of the problem says how far apart are the effective centers of positive and negative charge in a molecule of H2O. This is part A. Then part B. What is the maximum torque on a molecule of H2O in a typical laboratory electric field of magnitude 1.5 into 10 raised power 4 Newton per coulomb. And we have part C. Suppose the dipole moment of a molecule of H2O is initially pointing in a direction opposite to the field. How much work is done by the electric field in rotating the molecule into alignment with the field. This is our problem. Let me draw the figure. We complete the figure. Use another color. This is here hydrogen nucleus. This is another hydrogen nucleus. This is red one, oxygen nucleus. And this is the vector representing the electric dipole moment of the molecule, and this is our figure 1. Let me check the figure. Hydrogen nucleus, oxygen nucleus, and this is electron cloud in oxygen atom, and this is the electron cloud in this hydrogen atom. This is the electron cloud with another hydrogen atom. Let us check the problem and then discuss the solution. The problem says a molecule of water vapor H2O has an electric dipole moment of magnitude P equal 6.2 into 10 raised power minus 30 coulomb meter. Figure 1 is a representation of this molecule showing the 3 nuclei and the surrounding electron clouds. The electric dipole moment P is represented by a vector on the axis of symmetry. The dipole moment arises because the effective center of positive charge does not coincide with the effective center of negative charge. Then part A says how far apart are the effective centers of positive and negative charge in a molecule of H2O. Part B says what is the maximum torque on a molecule of H2O in a typical laboratory electric field of magnitude 1.5 into 10 raised power 4 Newton per coulomb. Then part C says suppose the dipole moment of a molecule of H2O is initially pointing in a direction opposite to the field. How much work is done by the electric field in rotating the molecule into alignment with the field? And this is our figure, right? So let us discuss the solution. First, we discuss part A of the solution. You know by definition what is an electric dipole. An electric dipole is a configuration of two equal and opposite charges separated by a certain distance. I repeat, a configuration of two equal and opposite charges separated by a certain distance, right? A configuration of two equal and opposite charges separated by a certain distance. That means if I have plus Q charge and a minus Q charge and they are separated by a certain distance d, this configuration of charges is called electric dipole, right? Now electric dipole, it is characterized by a vector called electric dipole moment. This vector is denoted by P. This vector has magnitude charge of either charge, magnitude of charge of either charge in the dipole, that is Q, and the distance of separation between the charges, which is sometimes called dipole length, D. So its unit is just charge into distance. So SI unit is coulomb meter, right? So an electric dipole is characterized by a vector called electric dipole moment. This vector has magnitude equal to charge of the either charge, magnitude of charge of the either charge, that is Q, and the distance of separation between the charges, D, which is sometimes called dipole length. So it's SI into Coulomb meter. Direction of this vector is, this vector points along the axis of the dipole. This is axis of this dipole. So this vector P points along the axis of the dipole, pointing from negative to positive charge. So this is the electric dipole moment vector of this particular dipole. So this vector lies along the axis and points from negative to positive charge, right? So let us move to this situation now. You know, hydrogen atom contains one proton in the nucleus and one electron in the extranuclear part. Its atomic number is 1. The atomic number of oxygen is 8. So it contains 8 protons inside the nucleus and 8 electrons in the extranuclear part. Now the structure of, so it has overall in the molecule 10 protons and 10 electrons, right? In the molecule overall. So when we have many point charges, then we talk of center of positive charge and center of negative charge. So it has some center of positive charge, some center of negative charge, but the centers of the positive and negative charge do not coincide in the molecule because of the structure of the molecule. So there is separation between the two centers and dipole moment is created. As you can see, the electrons in the hydrogen atoms are more lying more towards oxygen atom. So because of that, dipole moment is created along this axis of symmetry of the molecule. And the magnitude of that electric dipole moment is 6.2 into 10 raised to minus 30 coulomb meter. Right? I hope you got it. Now, our question goes like this. It says, how far apart are the effective centers of positive and negative charge in a molecule of H2O? That means we have to calculate the dipole length. That's easy. As I told you, there are 10 electrons and correspondingly 10 positive charges in this molecule. So we can write for the magnitude of the dipole moment P, which is QD, but Q is 10E times D, where you know E is the elementary charge, because there are 10 protons and 10 electrons in the molecules, so the charge of either charge is 10E. So we solve for D. D is P over 10E. P over 10E. P is given. What is P? 6.2 into 10 raised power minus 30 coulomb meter. Then we divide by 10, and the elementary charge is 1.60 into 10 raised power minus 19 coulomb. 1.60 into 10 raised power minus 19 coulomb. When we do the calculation, this turns out to be 3.9 picometer. 3.9 picometer. Remember, 1 picometer is 10 raised power minus 12 meter. So it is 3.9 picometer. This is the answer of part A. This is the separation distance between the centers of positive and negative charge in case of H2O molecule, right? As always, check the calculation at home. So let us move to the part B of the solution. So let me use the next page. In part B, you know, when a dipole is placed in some electric field, that there be some electric field in certain space. Now you place some electric dipole in it, represented by this P, then this electric field exerts torque on this dipole, and that torque is given by the cross product of P and E. So the magnitude of the torque, as you know, the definition of cross product of two vectors is the magnitude of P times the magnitude of E into the sine theta, where theta is the angle between P and E, right? Now part B says, what is the maximum torque on a molecule of H2O in a typical laboratory electric field of magnitude 1.5 into 10 raised to 4 Newton per coulomb. So we have to calculate the torque magnetic field, electric field is given. So let us solve. Now, as you know from this expression, torque equal to magnitude of torque is equal to P sine theta. So the torque is maximum for a given dipole in a given electric field when theta is 90 degree, right? Because for theta 90, sine theta has maximum value of 1. So the torque is a maximum when theta is equal to 90 degrees. So substituting the values in this expression, torque, magnitude of torque is PE sine theta. P is given 6.2 into 10 raised power minus 30 coulomb meter times the electric field, external electric field, which is given 1.5 into 10 raised power 4 Newton per coulomb times the sine of 90 degree, which is 1. So when you calculate it, this torque, the maximum torque, turns out to be 9.3 into 10 raised power minus 26 Newton meter. This is the answer of part B. Let me check it. PE sine theta, P is 6.2 into 10 raised by minus 30 coulomb, 30 coulomb meter. E is 1.5 into 10 raised by 4 Newton per coulomb. Sine 90 is 1. When we do the calculation, it turns out to be 9.3 into 10 raised by minus 26 Newton meter. As always, check the calculation. Let us move to part C. Part C says, suppose the dipole moment of the molecule H2 is initially pointing in a direction opposite to the field. That is, situation is like this. We have some electric field which is given. Now initially the dipole is placed this way. That means it is oppositely directed to the applied field initially, right? Then the question says, so dipole moment of molecule of H2 is initially pointing in a direction opposite to the field. How much work is done by the electric field in rotating the molecule into alignment with the field? So the electric field will act on this dipole. We are asked to find the work done by the electric field on this dipole in turning it parallel to the field. That means to this situation. This is final situation. So let us move to the calculation. Now the work done, let me use some other color. The work done in rotating the dipole by this field from theta naught to theta is given by, where theta naught is the angle between P and E in the initial configuration, and theta is the angle between P and E in final configuration. Expression is PE cos of theta minus, cos of theta naught. This is our expression. So if the initial angle between P and E is theta naught and the final angle between P and E is theta, then the work done by the electric field in turning the dipole from theta naught to theta configuration is given by PE cos theta minus cos theta naught. Now in our case, what is theta naught? Theta naught is 180 degrees, because initially P and E are oppositely directed. So theta naught is 180 degrees, and theta, the final angle when P and E are aligned, is 0 degrees. So let us put the numbers. So when we put the numbers, we get PE cos 0 degree minus cos 180 degrees, which becomes PE cos 0 is 1 minus cos 180 is minus 1. It becomes 1 minus minus 1 is 1 plus 1, which is 2. It becomes 2p, right? Cos theta 0 minus cos 180 degrees. Cos 0 is 1, 0 degrees 1, cos 180 degrees minus 1. 1 minus 1 is 1 plus 1, which is 2. That is 2p. So let us put the numbers. So W is twice PE, which is 2 times, then we have P 6.2 into 10 raised power minus 30 coulomb meter times electric field is 1.5 into 10 raised power 4 Newton per coulomb. When we do the calculation, it turns out to be 1.9 into 10 raised power 25 joule. This is the answer of part C. Let me check it. 2 times 6.2 into 10 raised power minus 30 coulomb meter times 1.5 into 10 raised power 4 Newton per coulomb. When we do the calculation, it turns out to be 1.9 into 10 raised power minus 25 joule. Check the calculation. This completes our problem. Let me summarize what we did. So we have hydrogen molecule which has electric dipole moment. Because of its structure, the centers of positive and negative charge does not coincide. So now this dipole is placed in the electric field, and we are asked first to find the distance between the centers of negative and positive charge, that is dipole length in this dipole. Then we are asked to find the maximum torque on the dipole in the given field. And then we are given the initial orientation of the dipole in the field, which is P is oppositely directed to the field, and we are asked to find work done by the field in rotating the dipole into alignment with the field. So we used the required expressions and solved for the dipole length, then maximum torque, then the work done by the field in turning the dipole from anti-parallel situation to the parallel situation with the field. So I hope you are enjoying these problems. This is all for today. Don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.